So, hi, we are now continuing with our discussion of spherical accretion, right. And remember, we have in our discussion, which encompassed both the solar wind and accretion, where we were discussing things like this kind of diagram. You will doubtless remember this kind of diagram, right, where this is the sonic point. We've already discussed, what leads to these kinds of transonic solutions. Both of these are transonic solutions because they pass through m square equals 1, and we discussed that this is representative, this kind of solution is representative of the solar wind and this of accretion. Both spherically symmetric and steady accretion, steady in the sense d over dt 0. So, we are now discussing this solution, right. So, we won't bother so much about going over the behavior of the slope at this point and what the sonic point means and everything, because we have already discussed these things. From what we discussed last time, you remember we were placing a lot of emphasis on the accretion rate. M dot, which is in units of grams per second, right, or solar masses per second. It's like grams per second essentially, and we discussed the fact that and why is accretion important in the first place? Well, accretion is important because it's a means of converting gravitational potential energy into observable photons, in the sense that it's a means of extracting gravitational potential energy. It's a very efficient means of extracting gravitational potential energy and likely converted into, via heating, converted into observable luminosity. And photons are what we observe in astronomy, which is why it's important to think about accretion problems, right. And the next thing we talked about is, well, you accrete one proton and you release so much. You release so many ergs of energy, right? So many ergs per second of energy. How about you accrete many protons? In other words, how about you increase the accretion rate? Well, attractive as it might sound, there's a limiting value to the accretion rate. Okay, you can only accrete so much matter, so that the amount of photons that are generated via the accretion process the radiation pressure due to those photons is not high enough to push the accreting matter outwards, and this limiting luminosity or this limiting accretion rate is called the Eddington accretion rate, right. So, as you can see, our discussion about spherical accretion places a lot of emphasis on this thing called accretion rate. Okay, and we will continue with that kind of accretion. We will continue with that kind of discussion. We will continue with our discussion of accretion rate in the context of steady spherical accretion. Okay, so now the most naive, the most natural thing to consider is a situation where if the gas, you have a central body sitting here, and the question is how much matter is it able to attract from infinity, right. So, but if the gas at infinity is cold, okay, i.e. the sound speed, and from now on I'm using A for sound speed instead of CS squared. So, simply because the references that I'm using say the same thing, right. So, the sound speed at infinity it tends to 0. Why is this? You remember the formula for sound speed, A square is equal to dp d rho in it's something like p over rho, and this is equal to rho over mp, this would be n k Boltzmann T over rho. So, essentially the sound speed goes directly as the temperature, well, the square of the sound speed goes as the temperature. So, if the gas is cold, the sound speed is also 0. Okay. So, if the gas at infinity is very cold, in other words, the sound speed at infinity goes to 0, right. If A infinity goes to 0, i.e., the Mach number at infinity tends to infinity. Here this subscript infinity simply means a very large distance from the central object. Okay. Then in that case, and this was the first kind of the first kind of considerations that were done with regard to quasi-spherical accretion. Then if we define a kind of an accretion radius, this is just a definition where this R A is an accretion radius. Okay. If this is defined as 2 g m star, where m star is the mass of the central object, over v infinity squared. Okay. So, the gas has a velocity at infinity you have a density rho infinity and a velocity v infinity. This is the assumption, and A infinity it tends to 0 at infinity. So, if we define this kind of an accretion radius, this has the dimensions of length, you can verify this. If we define a quantity called R A, which we call the accretion radius, then and the reason for calling this the accretion radius will become apparent immediately. Then the m dot would be equal to pi R A squared rho infinity v infinity. Okay. And from here, logic of calling this R A is immediately apparent, except for a factor of 4. It was a factor of order unity. This is like the area of a sphere of radius R A, and then you have it's as if matter with density rho infinity and v infinity is falling onto a sphere with the radius R A, and that is the accretion rate. Okay. But this is the accretion rate for absolutely cold matter, where the Mach number, because the sound speed tends to 0 and you have a finite velocity at infinity, the Mach number naturally tends to infinity. So, this was one way of thinking, until of course it was realized. Now, another way of saying that the sound speed tends to 0 at infinity is saying that the pressure at infinity is essentially 0. Why? Well, because the sound speed is essentially pressure over density. You have a finite density, so if the sound speed tends to 0, then the pressure also tends to 0. Well, is this a very realistic thing? Not really. Okay. It is hard to think of a situation where the pressure of the interstellar medium, and no matter how far it is from the central object, is actually 0. Therefore, modification was introduced by due to Bondi, Hermann Bondi, famous paper in 1952, okay, where he proposed that the P infinity, the pressure at infinity, and the sound speed at infinity are not 0. In other words, the gas is not cold at infinity. Okay. And in this case, if we now propose again a radius, an accretion radius, along the same kind of logic. Okay, R, we call this RB for R Bondi, and then you will have the same numerator, except here instead of V infinity square, I am going to have A infinity square. Okay, so we define a new accretion radius RB as over A infinity square. Now notice the similarity between this formula and this formula. It's exactly the same, except at the denominator you do not have V infinity square, you have A infinity square, and there's a reason for this. Okay, there's a reason for this. It will become apparent in a minute, but the immediate upshot of this is that the accretion rate is now there's a factor of order. This is a factor of dimensionless number of order unity. This is not so terribly important for the purposes of our discussion. I've just written it down for completeness, but it's essentially the same thing. It's like a 4 pi r squared, except now instead of R A you have R B squared, rho infinity and A infinity. So it's as if gas with a speed that's equal to the sound speed at infinity and density, which is some density that exists at infinity, is impinging on a sphere with radius r sub b, and the amount of matter that's coming through the sphere per second, that is the accretion rate. Okay, and in this case what we are saying is that as you go to infinity, we are talking about this kind of solution, right? So as you go to infinity, very, very large r, the velocity is essentially 0, although the sound speed is finite, right? Therefore, in this kind of situation, what happens is the Mach number at infinity is not infinity. In fact, the Mach number at infinity tends to 0, and that's what this kind of solution is representing. Okay, and therefore this kind of solution is due to Bondi. Okay, all right. So that's that, and now let us discuss a couple of other interesting phenomena that are that arise from this kind of consideration. Okay, why is this called an accretion radius? I mean, so on and so forth. Now, the main thing to note is that if the accretion is transonic, and what do I mean by transonic? I mean like this. Okay, if the accretion is such that you start with a very low Mach number, pass smoothly through a sonic point, you're subsonic all the way here, and you pass smoothly through the sonic point and then becomes supersonic. If the accretion is like that, then m dot can be uniquely determined by the sound speed at infinity and the density at infinity. That is evident from here. You see, the sound speed at infinity and the density at infinity. Although of course you have this Rb squared, but this Rb squared also involves just the sound speed at infinity, you see. So therefore this statement stands. You give me gas that is pretty much stationary, okay, at infinity, and you tell me what the sound speed is at that very large distance, this one, and you tell me what the density is at that very large distance. I will tell you what the m dot is. I'll immediately tell you what the m dot is. Okay, if it's a transonic flow, and it also turns out that this kind of m dot is the maximum possible m dot. And this is a very important statement. This can be shown, but it involves a little bit of mathematics that we don't really have time to go into. I urge you to look into the following paper. I urge you to look at (1996) physics reports. Okay, the proof of statements like this, the proof of this kind of statement is given in that paper, and a lot more. Okay, so that's a very comprehensive review article. I strongly urge you to this article is a very comprehensive review article. I urge you to look at it. But let's for a moment not bother about how to show this, but let's think about the implication of this. This is why we are so interested in transonic accretion. You see, from what we've been discussing since the last time we met, it should be apparent that you are really always interested in maximizing m dot. Okay, you really want to pile on as much m dot as possible. Okay, because that's going to give you the maximum possible luminosity. Okay, so there's a problem. You cannot pile on more than the Eddington limit. Yes, there's that, but nonetheless, so that's a limitation from one point of view. That's a maximum. Okay, but another point of view, you still want to maximize it to the extent possible without exceeding the limit, Eddington limit, and this is a way of achieving the maximum possible m dot. What is it? To ensure that the accretion is transonic. Okay, if you ensure that the accretion, the path, the accretion is transonic, then you're guaranteed that you are accreting the maximum possible m dot. You cannot have an m dot that's larger than this. And then of course you have to ensure that this maximum possible m dot is still lower than the Eddington limit. Otherwise, and for spherical accretion, turns out that itself is not a problem. Okay, all right. So this is one interesting statement, right? And I assured you that we would be talking a little bit about what's called the Bernoulli integral, and here we go. So a lot of this can be found in this paper. So remember, the Bernoulli integral this is essentially the specific energy. Okay, this is obtained by integrating the momentum equation, which we've written down many times before, especially in this context, in the context of quasi-spherical accretion. Okay, and you integrate that, and the result would be something like this. This is the kinetic energy per gram, and this is the internal energy per gram, and this is the gravitational potential energy per gram. Okay, so this would be at any given r. Okay, now, and this is conserved. You agree that's the whole point of the Bernoulli integral. This is conserved. This is the same at any r. No matter what the r is, the various terms will balance each other so that the sum is always the same. Now, what would this term? So this would be equal to whatever its value is at infinity. And what would be its value at infinity? Well, at infinity, the gravitational potential is essentially 0 because r is very large. So this essentially goes to 0. And we've said that at infinity, the gas is essentially at rest. Right? There's really no V infinity. Okay, so the gas is pardon me, I'm switching between U and V, but you get the context, right? So the gas is essentially at rest, so this is not there. Only this term survives. So this would be equal to A infinity squared over gamma minus 1. Okay, this immediately gives you a relation between A infinity and the A at the sonic point. Okay, the constancy of this, okay, immediately gives you a relation between the A infinity and the A at the sonic point. So it's like okay. Sorry, this is not into, this is actually this is a multiplication. So, again this is again the Bernoulli integral, and the Bernoulli integral at the sonic point is this. Why is that? Because at the sonic point, you know, there is no need to write a separate u, because by definition the u is equal to a. Okay, and there's a relation that expresses the r in terms of a, right, at the sonic point. That's a whole point, right, du dr it becomes a 0 over 0. So, this again is a Bernoulli integral at a infinity at the sonic point, and that can be immediately related to a infinity, right. And so, what this is essentially saying is that you immediately have a relation between a infinity and the sonic. Having prescribed a infinity and rho infinity, you know everything else. That is what I am trying to demonstrate here. Okay. You can immediately also have a relation like this. The rho, right, the rho at the sonic point is equal to the rho infinity, okay, times 2 over all of these formulas I am simply writing down. It is really no sweat to derive any of these using what we have done earlier. Okay. So, this now gives you transonic accretion rate, which would be m sub t equals 4 pi some function of gamma. Okay. There are lots of gammas floating around, and we won't bother too much. G square m star square rho infinity over a infinity cubed. And this, by the way, if I am writing m star there, I really should be writing m star here also. Okay. So, now this formula is essentially the same as this formula. Okay, it is essentially the same. There is really no difference. Okay, I might as well write a subscript t here. Okay, it is the same formula, and it is just written in a slightly different guise. And the point is, this is the maximum possible accretion rate. Okay, and the maximum possible accretion rate is achieved by ensuring transonic accretion. This is the same as writing equals, right, 4 pi lambda, where this lambda and this are pretty much the same thing, RB squared rho infinity a infinity. Okay. This and this are the same thing. Now, let us also look at a few interesting facts about this accretion radius. The accretion radius is the radius below which the density and sound speed increase significantly. So, up until the RB, the density and the sound speed are pretty much the same as what they were at infinity. It's only within this RB that the density and sound speed increase significantly. Okay, and and the other thing is for R much smaller than RB, the infall velocity goes as r raised to minus 1/2. For R much larger than RB, the infall velocity goes as r raised to minus 2. Now, what's this saying? You see, you have infall, okay, and it's falling in, but by the time it's falling in at a certain rate, okay, but by the time you cross this accretion radius, the infall rate sort of slows down. This is a sharper exponent than this one, right? And so, and for this here, the temperature is proportional to r raised to minus 1. So what happens is, below the accretion radius, the infall velocity kind of slows down and the density and the sound speed increase significantly. And as a result, the temperature increases. The temperature is no longer the same as it was at infinity. The temperature increases as r raised to 1 minus 1. And things of course blow up when you reach r equals 0. That is because we are considering a Newtonian potential, a Newtonian potential which goes as 1 over r. In reality, especially for a black hole, we need to consider general relativistic effects, which are quite complicated. Okay, but at least for a non-rotating black hole, it's sufficient for a non-rotating black hole. In order to mimic general relativistic effects, it's sufficient to replace the 1 over r potential that we've been using all throughout, this kind of potential. It's sufficient to replace the 1 over r potential with a potential that goes as 1 over r minus 2 gm over c squared. It's sufficient to replace this. That kind of mimics the general relativistic effects to a satisfactory extent. I don't have time to go into why this is so. This is what's called a pseudo-Newtonian potential. Okay, and now one last topic before we wrap up. Is transonic spherical accretion always smooth? In other words, always shock free? Okay, in order to understand this, and that's what it certainly looks like, right? In order to understand this, let us look at this now. You see, this is transonic accretion, right? So you have one sonic point, right? And now suppose there was a shock, right? Let's say, and by definition, by the time you accrete, the gas has to be supersonic. There is no other way. Okay, the boundary condition at very small radii has to be Mach number larger than 1. There's no other way. Okay, so suppose there was a shock, and the shock will always happen after the gas becomes supersonic. In other words, it will happen after this critical point, after this sonic point, right? So suppose there was a shock here. What does the shock do? The shock makes the supersonic flow transition to a subsonic flow. So you would have this curve, you would drop down to a value less than 1. But now you see, and then you cannot accrete anymore. You cannot accrete onto the central object anymore in a smooth fashion. That is not possible. Okay, because the inner boundary condition demands that at very small radii the flow is supersonic. Therefore, if you insist that there is a shock here, there has to be another sonic point through which the flow passes, and therefore the flow becomes supersonic yet again. Okay, if you need to have shocks, if shocks have to be present, you need multiple sonic points, not just one. Okay, one sonic point will not do, and multiple sonic points are generally not possible in spherical accretion. It is possible only if only if the polytropic index, okay, is not constant throughout the flow, but the polytropic index is a function of distance. If you vary the polytropic index, in other words, what you do is if you include additional sources of heating and cooling such that the polytropic index does not remain constant, at whatever value it is, it does not remain constant. If you make it vary as a function of R, then it's possible to have multiple sonic points, and then it is possible to have shocks. Okay, so this is all I have to say for now, and we will stop. Thank you.